All right, the second and shorter video I just want to follow up on 3 points related to that stuff I talked about earlier. So basically, some ways in which we should be a little bit skeptical or critical thinkers when it comes to interpreting scientific results, but also implications for research design if you ever do research yourself, or if you just want to be able to make sense of other people's research. Sometimes research design or interpretation issues go along with understanding statistical stuff. So I'm going to talk about 3 things in this video. The first one I'll talk about is what's called external validity. So basically, even when our results are true, in other words, imagine we did no type 1 error, no type 2 error, we found an effect, we found a real effect, we rejected the null hypothesis, and that's a good thing because there truly is an effect there. Even if we found that, let's say we found some results in the lab that showed that getting more sleep made you have a better sense of smell than if you're sleep deprived and your sense of smell is worse, right? And we showed that in, like, let's say a well-controlled sleep laboratory where we had really good what's called internal validity. So we designed the study really well to show that one thing really is causing the other thing. Even if that's the case, we may have shown that in the laboratory, in that specific setup, sleep is causing smell to be different, or sleep deprivation is causing your smell to be worse. But that may only apply in the lab. So the idea of internal validity is whether one variable really is leading to the other within those laboratory circumstances or within the setting that we're testing it. External validity is more the question of, do the results you found in your study really generalize to similar situations in the real world? So this isn't as much about statistical generalization, right? That's just inferential statistics. We already do inferential statistics to test whether our sample statistically represents the general population, but this is more about the circumstances or the setting in which you tested those variables in, like, a laboratory or in controlled setting. Does that same kind of relationship between the variables hold when we go out into the real world and look at more complex or varied circumstances? So do you only find that effect in a carefully controlled lab, or will it actually show up everywhere? That's the idea of external validity. So if your results do not apply to other people or places, then we'd say the results lack external validity. So your conclusion about the causal effects of sleep on smelling ability, or whatever you found in the lab, even if those results were valid within the lab, they may not hold true in other populations, other people than the type of people you looked at, or in other places. So if you did your study in one culture, you may find that in other cultures that relationship isn't true. That would be an issue of external validity. So I want to give you an example from a real study that was done not too long ago. So my question to you is, first think, what percent of drivers, like just in reality, what percent of drivers are in the top 50% of drivers? I'll give you a second. This is kind of a trick question, but like the answer is right there. What percent of drivers are in the top 50%? Well, it has to be 50%, right? Only half of people can be in the top half of skill in driving and in whatever, in anything we talk about. However, psychology research has asked people, do you think you're in the top 50% of drivers? Do you think you are an above average driver? And when we ask a whole bunch of people that question, what percent of drivers think they're in the top 50%? It's about 88% of people. So almost 90%, almost everyone thinks they're an above average driver, even though that's impossible. Only half of us can be above average. So this is a cognitive bias. It's called the better than average bias. It doesn't just apply to driving. It applies to every skill, including teaching. Half of teachers think they're above average. Half of stock market investors think they're above average. Like, humans just seem to have this bias, this cognitive bias of thinking we're above average, even when that we're not necessarily. So in the study I'm going to talk about, this study that I say may lack external validity, this study first explained that cognitive bias, the one I just talked about. They explained that cognitive bias to people. They said, hey, everyone tends to overestimate how above average they are at various skills. They explained the whole thing. They showed a bunch of stats and results to people. And then they asked people if those participants think they're more or less susceptible to that particular bias, to the better than average bias. So basically they ask people, okay, now that you understand what the better than average bias is, Everyone tends to overestimate. Like, a lot of people think they're in the top 50% when they're not, and here's why that doesn't work. They explained the whole thing, and then they asked people, do you think you're more susceptible to that bias than other people or less susceptible? And almost everyone thinks they're less susceptible than average. In other words, almost everyone thinks they're in the top 50% of critical thinkers, even though, again, that's impossible, right? Only half of us can be in the top 50%. So it's a little bit ironic, and that study that showed this, the study that did this last part here, they called what they found the bias blind spot. So people seem to be blind to the fact that they're biased, blind to their own biases. And they showed this for other biases as well. But that's kind of a funny example. Okay, it's a cool study. It made the news because it's one of those things that shows a limitation to human thinking, which a lot of the time psychology researchers are like, look, we're not as rational as we think. And here's another example of that. And that is interesting. It's newsworthy. However, if you look at the details, how was that study done? The one that demonstrated this bias blind spot in people, how was the study carried out? If you look at the details, they just tested 24 college students at Stanford, which may not be very representative of everyone out there, right? But they tested 24 college students at Stanford and just assumed that those students were representative of everyone in the population. So they made conclusions about humans in general having a bias blind spot just because these 24 college students at Stanford had that problem. So maybe those 24 college students at Stanford actually really were just above average at avoiding cognitive biases relative to the rest of the human population, right? Because people who get into Stanford are probably higher IQ on average. There's selection effects there. So maybe there wasn't actually a mistake. Like, maybe we took that study too seriously because we didn't go and test a bunch of humans, a bunch of random humans. So the sample in this case that was tested, the people they used in their sample, didn't accurately represent the general population of all humans. So really, if we read about the results of that study, we should take it as a study about college students at Stanford or college students in really selective schools, not necessarily as results about all humans, until we go and replicate this with other populations. So I'd say this original study lacks external validity until we go and repeat it with other populations. Now, this is a bigger problem than you think in psychology, as well as other fields, but specifically in psychology, this is a big problem. We actually tend to use college students in most studies that we do of psychology across the nation, even across the globe. Most studies are done on college students, and that's done because college students are what's called a convenience sample. It's really easy to get college students to take a survey, do an experiment, come into a laboratory and try something out, and that's because it's become the norm. It's very common in Psychology 101 classes to give students the opportunity to participate in research as participants. In other words, to volunteer and participate in studies to get a feel for research, how it's done, to get a research experience. And that also provides the data, it provides the sample for us to test all sorts of psychological hypotheses and for people to publish all sorts of studies. But even when we go out and do what are called community samples, when we don't study college students, when we don't do a convenient sample, but actually try and get representative people out there in the real world, community members, in other words, to participate in our studies, we bring them off campus, we bring them into our laboratory to run through the study or whatever it is. Even when we try to be more representative, we tend to vastly overrepresent or overselect what are called weird people. So the scientific literature about psychology is actually a literature about weird people. What do I mean by weird? This is an acronym. It means people from societies that are Western, educated, industrialized, and rich democratic nations. So weird nations, people from Western, educated, industrialized, rich, and democratic nations. Those are the people that are showing up in all sorts of scientific results about psychology that we use to make conclusions about humans in general, but that may not actually represent all humans. So just to give you an example, people have quantified this. About 93% of studies in the biggest psych journals, almost all studies used only Westerners as their sample. And 99% of participants in psychology studies in the United States, and even 80% in other Western nations, but in the United States, almost 100% of the people we study in psychology studies are undergraduate psych students. And that is absurd when you think about the fact that those people may not represent humans in general, right? They may not be representative, and so our conclusions about psychology don't necessarily generalize to everyone. They don't necessarily have the external validity that they're given when we write up those results and publish them as conclusions about psychology in general. Just to give you an example of how we know this can lead to mistaken interpretations, how these results may not hold up in other cultures. There's been a lot of research in what's called game theory or behavioral economics, looking at or using a procedure called the ultimatum game. So it's like a game theory game, kind of like the prisoner's dilemma. In the ultimatum game, what you've got is two people, and one person is given a bunch of money. So let's say they're given $100. And in this game, that first person who has the $100, they have to offer some amount of that to a second player, a second person in the game, some other participant who they don't know. They have to offer some of that $100 to the person. They can choose how much. They can say, I want to do a $99, $1 split and offer $1 to the other person. Or they can say, I want to do a 50-50 split where we each get 50%. Or they can come up with some other number. Here's the thing though. Then the way the ultimatum game works, then the second player has to choose, do I accept the offer or do I reject the offer? If the second player accepts the offer, if they think it's reasonable enough, then both people get to keep that money. So let's say player one offered a 66%, 33% split, where they keep $66, the other person gets $33 or $34, right? The rest of the money. If player two says that's fine, that's okay, and they walk away with their $34, the first player gets to keep their $66. But if player two says, that's not very fair, I don't like that, or you only offered me $1 and you're keeping $99, then player two can reject the offer. If they do that, no one gets anything, which means player one has screwed themselves out of any money by being too greedy. That's the ultimatum game, okay? This has been used a lot to study choice and decision making and social cognition and things like that in psychology. The ultimatum game is used a lot. What we know is when we look at people doing the ultimatum game, like what they offer. For example, we put them in an fMRI scan or do a brain scan while they make a generous offer or a less generous offer when they're being greedy or altruistic or whatever it is. You know, we make all these conclusions about human psychology using the ultimatum game. Turns out in Western culture in the US versus some other culture, like small isolated cultures or cultures where gift giving is a very common cultural norm, it's used as sort of a way of currying favor, we find very different results. So in some cultures, what we get is less than 45%, like offers tend to be like pretty small. You're offering quite a bit less than half to the other person. Whereas in these gift-giving cultures, you get offers sometimes where they're giving the other person more than half. They're offering more than half to the other person. So all our conclusions, based on hundreds of studies that have been done on the ultimatum game, based on like the U.S. population, we make these assumptions about how people, how greedy or altruistic people are in general. But we have no idea that there are other cultures out there where people's behavior is very, very different, and thus their cognition might be different, and the results we get in a brain scanner might be different. All of those things we only notice if we take into account that those original studies may have been lacking external validity. It's not that they're wrong about the population they're studying. They may be correct about the population they're studying, but because they only sampled from, let's say, weird participants in the Western world, then their results only apply to weird participants in the Western world. They didn't sample from all humans equally, and so they don't get to generalize their conclusions to all humans in general. So we often claim that psychology is the study of the human mind, but so far it's honestly mostly just the study of weird students, right? And so we've got low external validity if we want to make conclusions about human minds in general. The biggest solution here is cross-cultural psychology. It's actually a subfield of psychology. It's become a growing field where we go out and do these studies across a bunch of different cultures and try and figure out what is human universal and what differs depending on where you live or what culture you've grown up in. And often we do find differences. Not always. Sometimes we don't. For some basic perceptual things, like how the sensory and neural systems work, it's the same across all humans, but you'd actually be surprised. A lot of the ways our brain interprets things, even in terms of what colors we see, our ability to perceive two different blues, shades of blue being different blues. Like the language we speak and whether we have different words for different shades of blue actually affects how quickly or how accurately we can detect differences between subtle shades of blue. So that's an example where the culture, the language you grew up with, affects even a basic perceptual phenomena. So this is why the field of cross-cultural psychology is so important, so that we can start to generalize and get more external validity. And then, of course, probably the biggest step, even without looking across other cultures, is just replicating studies using non-students. So maybe in those original studies, we find some basic results in the convenience sample of students, but now it's becoming much more common for journals that are interested in publishing results to say, hey, have you replicated this in a community sample to show that this applies to people who are older than students, people who have a different socioeconomic status than students, people who are different than those in your college classroom. And so we can improve external validity. We just have to note that this is a problem. However, we also have some other problems creeping in here. So we have problems simply by studying the people who happen to be willing to volunteer for studies. So here's an example of this. This is a study back in 2010. We had known for a while about the weird participants issue, that's a problem. So we have gotten better about that. But someone found there's also an issue with how and when people who decides to volunteer for our studies. So at this one school, they had a whole bunch of undergraduates at Michigan State, a whole bunch of undergraduates who had the option to participate in a study, to volunteer for a study. And there were two versions of the study that they set up: an online version where they did a kind of personality survey, or a face-to-face version where they actually had to go into a laboratory to do it. Now, in both of these cases, they did the study at Wednesdays at 12:30, so it's the same time, same day of the week and everything. The same personality survey was administered on a computer in the exact same way. So the only difference was the people who chose to go to the face-to-face version or the online version. And of those, it turns out that the people who opted to go to the laboratory, who volunteered to go in and do the lab task, they were not necessarily representative. They weren't the same as the people who did it online. So those who did it in the lab were more likely to be high in extraversion as a personality trait, to be more extroverted. Now, the effect size wasn't that huge. We know that a Cohen's d of around 0.2 or negative 0.2. It's not a big effect size. It's a pretty small effect size, but it's statistically significant. It's about a quarter of a standard deviation difference between the two groups. But that means that people who come into our laboratory will tend to be people who are a little more extroverted than normal. And that means any results, not just for personality stuff, but any results where people come in and do a lab study, may be people that overrepresent extroverted people, and so it may not apply to everyone else who wouldn't have come in and done that study in the first place. And there's a bunch of other examples, like choice of when they do the study, early in the semester or late. The more conscientious students are the ones who did early dates earlier in the semester. Men were more likely to volunteer later in the semester than women, even when you control for average personality. And so they found basically, like, depending when we do the study, early and late in the semester, how we do the study, in person or online, those things lead to us getting a sample of participants that may not always be representative of everyone, that may be unrepresentative in specific ways. And if we don't account for that, then once again, our results are not necessarily going to represent humans in general. And also, we need to think about the importance of construct validity. So I've talked about internal validity as basically just the design of your study. Does it show causation? Did you design it doing a proper true experiment so you can show that one variable leads to the other? That's internal validity. And that, we might do in controlled laboratory circumstances so we can be sure about the causation. But then we have to check on external validity and see, does it actually apply to other situations and other people? That's important. But there's also construct validity, which is, does your operational definition, the way you defined the variables and measured the variables in your study, do they actually measure what you think you did or what you claim to have measured? And the problem is scientists often choose the measures that are easiest to use. In other words, things that are easiest to quantify and put a number to, even if they're not really measuring the construct or the concept that we're really interested in. So I like this joke from Saturday Morning Breakfast Cereal. It's a kind of nerdy comic on the internet. She says, wait, how do I know you're good at sex? And he says, I got an 87% on erotic reading comprehension. She says, what does that have to do with sex? And he says, nothing, but it's testable. And then at the bottom, the punchline, if sex was like standardized tests, I should say standardized tests. So basically, we often end up measuring things that aren't necessarily what we really care about. So yes, there's a measure for depression, or there's a measure for erotic reading comprehension, but we didn't necessarily measure depression using that self-report questionnaire, as well as other ways that, right, there might be better ways to measure depression. Or in this case, we didn't actually measure sexual prowess or skill. It's just an easy way to measure is give people this particular survey that's been used before. And that's a problem. We often end up coming to scientific results that are about concepts different than the ones we're actually talking about. And finally, there have actually been some recent papers even calling into question self-report in general. So there have been examples like in the clinical psychology literature showing that a lot of effects actually disappear when you start to check external or objective measures of things. So rather than just asking if someone is depressed by self-report or asking if they have psychosis symptoms by self-report, we can ask others like a professional or peers or family members or things like that about the symptoms. And sometimes we find that the results are very, very different depending on if we have some sort of check or look for some sort of more objective measure or just some sort of external measure that's not self-report. The fact is we get very different results when we look at self-report versus other ways of measuring things, and this means we should be careful about relying only on self-report. Now, the second thing I want to talk about in this video is, this will be a smaller one, but basically when we reject the null hypothesis on something like, let's say, an independent samples t-test or an ANOVA or whatever, but let's say just an independent samples t-test, we're comparing two different groups, we reject the null hypothesis, that means that we have found a statistically significant difference between not those two groups necessarily, but two population means. So if we're comparing the height of men and the height of women, we have found a statistically significant difference between the average height of men, right? This is a mu, this is an average, it means the mean, right? The mean height of men does not equal the mean height of my second group, the women group, right? And this is about populations, it's a Greek letter, right? A Greek letter mu. So it's about populations of men and populations of women, but it's an average score, right? This is the average of the population of men's heights and the average of the populations of women's heights. Now, the reason that we need to be careful about how to interpret that, I think, comes from, or can be seen if we look at this little joke button over here, statistics, a discipline that proves the average person has one testicle. Like, we may have found that the average man has a different number than the average woman. That's a population difference. It doesn't tell us about an individual person who may have had an accident or may have had something like that. We need to be careful to distinguish between summary statistics about entire populations and individual people within those populations who may or may not fit that pattern. So our statistics are only ever telling us about populations and generally about averages within those populations. We simply don't have much information on individuals when it comes to science. There are some studies that look at individual differences, and that's really important, but that is not the norm. Most studies look at group differences. They find overall there's a difference between men and women, or a difference between group A and group B, people with this personality trait and that, right? Introverts versus extroverts, dog owners versus cat owners. And we find those differences, or people who are in our experimental group but not our control group, right? Stuff like that. But that doesn't tell us about one individual person. So I want to give you an example why this is an issue. Let's say we do an experiment where we use proper procedure. We randomly assign people. In this case, we'll take 40 people and randomly assign them into two groups of 20. And group one will have them watch a violent movie. Group two will have them watch a non-violent movie that takes the same amount of time. So it's kind of my experimental group and my control group where they're doing something similar but without the violence. And then afterwards I'll measure aggression. And as we know, there are many ways we could measure aggression, like whether or not you punish someone in a competitive task with a loud noise or whatever it is, whether you get in fights, but we have some way of measuring aggression. So we've done a very basic experiment here. You randomly assign people into group one or group two, have them do these different things, the experiment versus the control situation, and then measure something afterwards and see if there's a difference. And let's say there is. Let's say we find a significant result. So the average aggression in group one, those who watched a violent movie, is larger than the average aggression of group two. we would usually take a conclusion from that study of saying, we have evidence that violent movies cause aggressive behavior. This is how those results would be written up. Maybe we would want to go back and replicate it with a larger sample size and do all those other things, right? But assuming we repeat this over and over, do the same procedure, we have got good evidence eventually that violent movies cause aggressive behavior, because we find that group difference, the average difference between a group, all the people who watch violent movies versus all the people that watch non-violent movies. But what about when when a specific one person watches a violent movie and then acts aggressively? So let's say we find that someone, commits a school shooting or something like that, and then we look at their past and see that they watched a lot of violent movies or played a lot of violent video games. Does that prove that the violent movies or the violent games or whatever it is caused that one person to act more aggressively? And actually, it doesn't. Logically, we cannot conclude that. We can't conclude that the violent movie caused the aggression for this one person from our results. Even if we know that in general, violent movies tend to cause, on average, higher aggression across a bunch of people in aggregate, that doesn't mean we know about causation for individual people. So we often make the logical error of taking these studies about people on average and generalizing them to individual humans and telling individual causation stories when we haven't actually shown that at all. So experiments give us the power to conclude causal things about causation, right? Not just correlation. If we do a true experiment, it does give us the power to make conclusions about causal influences in general between variables, but we can't apply that to an individual person's situation. Or it's not that it doesn't apply, but we don't always know for sure that it applies to that one individual. We know that the odds are it applies to them, right? If it applies to people in general, then the odds are it will also hold for that individual, but that's not always the case. So we could say kind of understanding psychology, maybe with a capital P, right? Understanding the field of psychology or the general rules of human psychology may not actually help you understand your own psychology. Which is why people who major in psychology thinking that it'll help them with, self-help with their own psychological issues is not necessarily a good idea, because you learn about human psychology in general, the general rules of human, but that doesn't mean it applies to you individually. Everyone's situation may have their own variants or variations there. Okay, and then the last final lesson I want to talk about for this stuff before I close this video is placebo effects. So you may think about placebo effects, usually the standard way of thinking about placebo effects is something we can control in studies like medical studies, where we give people pills to test if a certain drug, right, a certain medicine works or doesn't work. So you might give people in a pharmacology study 2 pills, right? You randomly assign people to be in 2 different groups, and some of them get the green pill and some of them get the blue pill, but in a double-blind study, which is the best way to do a study, a randomized controlled trial using double-blind procedure means that neither the doctors, the people actually giving the pill to the patients and measuring how well things go, nor the patients themselves know which pill they're getting. In other words, they don't know. They know they're getting a green pill, but they don't know if it's the actual drug, the actual medicine in there, or if they're getting the sugar pill, which is a placebo, basically an empty pill, right? So both groups don't know whether they're getting the placebo or the actual drug, and even the doctors don't know that, and that's why we call it double blind. The patients are blind to what condition they're in, and the doctors are blind to what condition they're in. We can only go back after the fact. Once we've got their unbiased results and compared these 2 groups, then we can unblind or unmask things and look up, were the green pills the medicine or were the blue pills, and see if it made a difference. So it's really easy in medicine to do studies that control for placebo effects. You may know placebo effects are like an expectation effect. If you're taking a medicine, you think it's going to work, it actually may make things a little better, especially for studies of things that help with pain, for example. We know the placebo effect causes the release of endorphins, which are our endogenous morphines, which can make pain go down. So if someone thinks they're taking a pain-relieving pill or putting on a pain-relieving cream or doing some fancy, whatever pseudoscience thing that allegedly makes pain better, or if they're in a field that hasn't been tested as well, but that claims that it's good, certain manual manipulation or hovering your hands over someone helps with chronic pain, that's where placebo effects are very common. Well, we can control for those placebo effects using something like this procedure. It's really easy in medicine, but that's really hard in psychology studies. Why? Psychology studies have trouble setting things up with a placebo control condition. We have trouble setting things up so that things can truly be double blind in its design. So we have trouble avoiding placebo effects. Let me give you an example. Let's say you want to test if brain training games actually work to improve cognition. This is certainly something people have been interested in. There's a hell of a lot of money to be made here. People have been making money without actually testing whether stuff works, right? They can just make the claims. They can say it improves your memory, helps stave off Alzheimer's. They can say all this bullshit without ever actually testing it. But let's say they want to, sell their product more. So they say, we're going to do a scientific study. We're going to test our brain training game to make sure it actually improves cognition. So here's what they might do. They might randomly assign people into two groups. So far, this is looking good. That's an experiment design, right? And the experimental group is going to complete a brain training game, which let's say it's some auditory tasks that adapt to participant performance to continuously challenge them. So they're doing the brain training games. The other group, the control group, let's say they just watch an educational DVD for the same amount of time. Or maybe even they just sit on their ass for the same amount of time. That's our control group. The problem is that's not like a placebo, because in the placebo control that I talked about with like drug studies, people don't know what condition they're in. So we're going to get equal expectation of improvement, equal placebo effects from both groups. They're both going to be just as likely to think that they're taking something that will help them, that will make them perform better, right? In this case, though, we haven't controlled for that. We have a difference between these groups. One group is doing the brain training, but this group might also, on top of that, have higher expectations. In other words, more of a placebo effect than the control group, who's getting this other non-brain training, right? That there are no brain training group, but the other difference is they might also have less expectation of getting better, which might lead to less motivation when we test their cognition later. So if we find an improvement in the cognition in general of the experimental group, it may be just due to expectations, not the actual brain training games. It might just be because they have different expectations among those two groups. That would be the placebo effect, right? So in other words, the placebo effect might be stronger for the experimental group, but it would still be just the placebo effect, not good evidence of brain training. So that company might go and publish this study and say, look, our brain training group did better than our quote unquote control group, but they didn't have a proper control group that accounted for the placebo effect. So that's a problem. Really, in something like psychology, if you want to truly show causation, show that brain training works or whatever it is, then you need more than just having a control group that's just doing something random. What you need is something more than that. You need an active control group, one that's doing something very similar to the other group. So here's a little flowchart that might be helpful. Is the intervention, the treatment you're comparing, is it compared to a control group? If the answer is no, then you should not, from the results of your study, saying that your treatment caused any sort of improvement or difference there, right? Because you didn't have a control group. So everyone kind of knows that. Most of us know there should be a control group in a good experiment. But let's say yes. Let's say there's a control group. There's a second question we need to ask ourselves. Is the control group active? So is the control group just sitting on their ass for 2 hours while the other group played the brain training game for 2 hours? Was the control group people who were just going about their lives for 6 months, whereas the brain training group was doing brain training for 6 months? If that's the case, then we have a non-active control group, and that's not a good comparison. To be a fair comparison, we need the control group to be doing something for the same amount of time. So if we say no, there's not an active control group, they were just sitting on their ass, they're not really a control group. It's not a good control group, even though the experimenters might say they had a control group. It's not a proper control. So once again, we'd say causation claim is not merited. We can't talk about causation in that case. What we really need to look at then is, if we have an active control group, how do we set it up? So if they're not just sitting on their ass, they're doing something else for the same amount of time, we actually need to set things up. To really talk about causation for our treatment, we need to set things up so the control group is doing something active that is similar to our treatment group, our true treatment group, in such a way that their expectations are the same or roughly equal for anything we're going to measure. You need to show that the control group has similar expectations as the experimental group, that they both think they're going to get better. They both think they're going to get similar improvement. If that's the case, then you've got equal placebo effect and you can rule that out. If you don't do that, though, then no causation claim is merited once again. And even if you have a control group doing something actively, they may still have different expectations, and it may still be the placebo effect is the explanation, not the actual treatment like brain training. And so it's really hard to design studies like this in psychology. You have to think of proper, good control conditions that are designed in such a way to make sure you've equated expectations, that you've got equal placebo effects in both of the groups, so that you know that's not an explanation if you do find a difference in your treatment group from your control group. So that's an example of one of the harder, this is a research design thing, but this is where it's hard to design good psychology studies that really do tell us about causation. And people often get lazy and they stop in one of the earlier stages of this flowchart, which means we really can't be as confident in the causation claims that we see sometimes. So anyway, these are just some things I wanted to bring up in these two videos about kind of limitations of research in psychology and other fields that we need to be aware of. As I said, these things are getting better. We're paying more attention to replication, the importance of replication of studies. We've always known that that should be the case, but now the scientific culture is starting to value that a lot more, and people are more likely in journals to publish replication studies, even though they might have been harder to publish before. We're starting to do more open access studies, so it's easier to see the science publicly without having to pay for it, but also open publication of data where people share the raw data so others can repeat their statistical analyses and double check their work. That didn't used to be the case, but now a lot of journals require you to submit the raw data so other people can check your answers and check your stats. There are other things like fixing peer review to make it more robust. It's still kind of our best way in science to make sure I have some other anonymous researchers who are specialists in the field look at your work and check your work before it gets published. That is very important. Peer review is one of the best tools we have in science, but as we've seen, there are some limitations to that methodology that we can improve on. For example, by giving the peer reviewers access to the data openly, then they can check those things before the studies get published. Also, like I mentioned, pre-registering trials. We do that for clinical trials now, where you have to say, this is the study I'm going to do, and this is how I'm going to carry out the analysis ahead of time, to minimize researcher degrees of freedom, to minimize those questionable research practices. That's very important. That is now becoming more common, especially in a lot of the big journals. And like I said, sharing raw data, letting people inspect your data, stuff like that. So anyway, these are things to think about as you interpret and maybe even carry out scientific research in the future, is realizing some of the limitations to what you might read about in the popular press. That doesn't mean we shouldn't take science seriously, but there's a difference between, say, things that show up in a textbook because we've spent decades researching it and confirming with replications that it definitely works, versus something that just came out in the news as a brand new study. It might be interesting and newsworthy, but you should have at least a little bit of skepticism or be able to look for some of those clues. Like, did they use an active control condition where we would have maybe equal placebo expectations between the groups, or did they not? Have other labs looked at this stuff? Did they publish in a journal that was open access and shares the data? Things like that might help you judge how seriously you should take an individual result until you've seen whether it replicates. So hopefully this was helpful, even though it's not, doing statistics yourself. It's thinking about some of the big picture effects of people like doing stats for their career, how it affects society and implications in general.